Hi everyone, today I'm going to show you some of the highlights and key points of Chapter 12. I'm not going to go extremely in depth. I just want to show you at a glance of what Chapter 12 consists of so that you have at least seen it a little bit. So Section 1, I'm going to touch on very, very briefly. Section 1 is about inference for linear regression, which means that this is a new set of confidence intervals and hypothesis tests for regression lines. And so the questions that we're asking are, is it really a linear relationship between the variables? And what is our actual estimate for what the actual slope is? Because we have this data over here that we can use to make predictions of what the slope might be, but what is the actual population parameter? And that's going to involve a confidence interval. So the idea here is that if I gather different data throughout different times, then I might get a slightly different slope. And so we want an estimate of what the actual slope is. There are conditions. I'm not really going to talk about them. I just want to pause on this slide very quickly to show you that I talked about S being the standard deviation of the residuals. So there it is. Here's how it's actually calculated. So here's our example we're going to be looking at. This is, we're letting a little toy helicopter drop and seeing how long it takes to drop and how long the flight is. So our regression line gives a slope of 0.00572444. And we can make an interpretation of what that slope means. You should know how to do that. But what we want to know is what's an estimate for the actual slope. There's a formula. Again, I don't want to go extremely into detail about it because your calculator will do that work. Or it'll usually have like a computer output that'll do that work for you. For example, right here. And so you would just, if you were to do this, you would just need to plug in the values that you needed out of the computer output and get an estimate for what the slope is. And then we can interpret. We are 95% confident that the actual slope of the population falls between these two areas. And this basically gives the same process of the four-step process of the confidence interval for estimating the slope of a regression line. That's what we're doing. And then the second part of this section is talking about a hypothesis test. So let's talk about that. Which is that we can do a t-test for the slope of a regression line. We have a null hypothesis, which is that the slope is some value that we hypothesize. And then the alternative is that the slope is greater than, less than, or not equal to. And most of the time, your null hypothesis is that the slope is 0. And that signifies that there's no real linear association between the two variables. Then your alternative is that the slope is not 0, so that there is some linear relationship. So for example, on this one, our null and alternative is going to be based on the fact that we're wondering whether there's a positive linear relationship. So based on that, our null hypothesis is that the slope is 0. Our alternative is that the slope is greater than 0 because we're wondering if the slope is positive. That's going to give us a positive association. Again, there are conditions. I'm not really going to talk about them. I'll just say again that the table would give you all the values that you would need. And just like before, we could get a p-value and make a conclusion. Hey, the p-value is 0.002. And that's less than alpha equals 0.05. So we're rejecting the null hypothesis. We're concluding the alternative. It's a lot of the same idea as our usual hypothesis tests. Except this time we're determining something about what the slope is and making a hypothesis about the slope. That's all I want to talk about for Section 1. Section 2 I want to talk about a little more because it's about scatter plots and data that isn't linear. So at this point, we've been talking about data that is linear. that we have a linear association. But we talked about how sometimes there can be some kind of curved pattern. And so let's talk about a couple of those examples, and I want to bring up a recent example. But first, pizza. If we had a diameter of the pizza versus how much area is taken up, that's not a linear relationship. So the going from 10 inches to 12 inches to 14 inches doesn't increase by the same amount each time, because the diameter and the area don't have a linear association, because an area of a circle is pi r squared. So that means you actually have a relationship between its diameter and x squared. And when that happens, then that's what's called a power model, a power relationship. And that means that we have some kind of quadratic or cubic relationship between the two variables. So one example is here in the relationship between the length and weight of the fish. And what we can do is we can play around with some different models and see which one fits it the best. And so what we're doing is we are seeing that a cubic relationship is going to help things the best. So what we're doing is we're graphing y on the y-axis and we're graphing x cubed on the x-axis instead of graphing x. And when we do that, then what we're really doing is saying that the relationship between x cubed and y is a straight line. Now, an easier way to do this is with logarithms. So I want to talk a little bit about logarithms and how we can use this to model exponential growth and logarithmic relationships. The first way that logarithms are useful is with exponential growth. Since logs are just another way of writing exponents, exponential growth can be used with logarithms. Here's how we can do that. So we have our general exponential model, y equals a, b to the x. We use b for the base, x is up in the exponent, our variable's up in the exponent, and a out in front, some constant out in front. All right, first off, let's take the log of both sides. And once we take the log of both sides, what that's going to let us do is to establish some patterns and properties of our logarithms. So one of the properties of logarithms is that if you have multiplication happening inside of the logarithm, log of a times b, you should know that that property is that log of a times b is log of a plus the log of b. So if I have log of ab to the x, that's the same as log of a plus log of b to the x. That's a property of logarithms. And another property of logarithms that is extremely useful for us is that if you have log of b to the x, if you've got something up in the exponent, then you can bring it out in front. And so it's also log of y equals log of a plus x times log of b. So with exponential growth, you want to graph x versus log of y. Now with a power model, if you have some polynomial, let's say like y versus x squared, or you have some power, and we can do the same thing, separate it as log of a plus log of x to the p, which I can take the power and bring it out in front. And now I'm graphing log of x on the x-axis and log of y on the y-axis. And so the power that's in the exponent becomes the slope of the regression line for log of y versus log of x. And so I want to recap that very quickly so that we're on the same page of what that looks like. Exponential, which is in the form y equals a b to the x, versus power, where we have y equals a times x to the p. So notice the difference here. Here the variable's in the base and we're raising it to some constant power. Here we have some base and we're raising it to a power. We're raising it to the x. So the variable is up in the exponent here. This turns into something where we graph x versus log of y. And that's an example that we'll look at in a second. If we have a power relationship where the variable's down in the base and we're raising it to some power each time, so like this is y versus x squared or y versus x cubed, then we have log of x versus log of y. Some examples of where we use logarithmic scales are with sound in decibels. That's on a logarithmic scale. The Richter scale for earthquakes is on a logarithmic scale. So there are a couple different places that we use this. But let me go through an example that's pretty relevant right now. I have some data here in the calculator. As I'm scrolling through, might make some speculation about what this data is. This data is the total number of COVID-19 cases in the month of March. So each of these is a date of March in the United States. And you'll see that this is clearly not linear. If you were to try and determine the slope, well, it looks like it's about 25. But then, as we go through, it's very clearly not 25 anymore. But if I go to my graph, I can see very clearly that this is some kind of exponential growth that's happening. So now, I can chart this data two different ways, and I want to talk about both of them and see what we end up with. Method number one is I can go over to stat and calc, and you'll notice that we've had linear regression, and that's what we used, but there's also quadratic regression, cubic regression, logarithmic regression, power regression, but we're going to look at exponential regression, which will give us an equation of an exponential model. I'm going to go ahead and store it in vars over to y vars function y1. I'm going to go ahead and store it in y1 and show you the graph. If you saw very briefly there, it is graphing a b to the x. So here's the exponential curve that it uses to fit the data. So we can use an exponential curve, and the calculator can come up with an exponential curve. But another way we can do this, if we want to make this linear, then I talked about how an exponential would be x versus natural log of y. That's what we would graph, or x versus the log of y. So let's graph x versus the log of y. So in list 3, instead of y, we're going to graph the log of y. The log of y is in list 2. And then I'm going to make a scatter plot that graphs list 1 versus list 3. Zoom 9. And you'll see that it's a lot more of a straight line. And that's the idea, is to fit this. When we talk about the logarithmic scale, we're talking about fitting this into a line, into a straight line, because we like lines. We don't like curved models. We generally like to see a straight line model. And so now I can just calculate a linear regression line, like I always do, of list 1 versus list 3. And keep in mind, when you see this graph, and when you see this equation, that this is really, it is not really y equals a plus bx. What is really happening is that we're graphing the log of y versus x. So really, this is the log of y hat equals 1.783 plus 0.11968x. And it should be stored into y1, right? So if I go to zoom 9 and hit my graph, then there should be a line. You'll notice that I charted the data for March. Now, we can talk about how there's a lot of things in the data that aren't here. For example, in March, we didn't have as many tests as we do now. And so we weren't testing as widespread. And they were different levels of testing in different areas depending on where you were. There are a lot of people that don't have symptoms that still have the disease and all that kind of stuff. A lot of things that you probably haven't heard the end of for the past month. But just things to get in your head that we want to be mindful about the data. And another way we want to be mindful is extrapolation. I want to show you this as an example. If I wanted to use this model to predict anything outside of March, let's look at what that would look like. So today is May 4th, as I'm recording this, and that means that it is day 65 on this table. So if I use day 65, get ready. Make your prediction now as to what if it will happen if I plug 65 in. It's going to be big. I don't know what it is yet. But let's look. Vars, over to yvars, function y1. If I use this and I plug in 65, this would predict that the number of cases in the United States today would be that. That's 3 trillion. Which, as you know, is more people than there are in the world. By a lot. So just keep that kind of thing in mind. And the reason that this doesn't work is because the curve levels off. People recover and then they can't get infected anymore. We put social distancing stuff into practice. Once it starts to infect a community and people get infected, the curve does level out at a certain point. And where the curve levels off at is what we've been trying to flatten. And I posted an article a couple weeks ago about that and about what that means and why we're putting these practices into place. But just an example of extrapolation where we don't want to use this data from March to predict what's going to happen in May 4th, because May 4th is not in March. All right, so that gives you an idea of what Chapter 12 looks like and what it covers. The most interesting thing I think in here is the nonlinear patterns and fitting it to a scale that lets us make it linear. That's kind of the key idea of the last section of this chapter. Again, this is not on the AP test, but the expectation for AP is that we cover it at least a little bit to give you an idea of what it looks like. So I wanted to do that. Plus, it is relevant to things that are going on right now, which is the other reason I wanted to talk about it. So that's all for now, and I'll talk to you more soon. Take care.